All right, let's go. Okay, so this video might be a little longer, but that's because this is such a fundamental part of geometry. Geometry, to me, is really the study of pure logic, and this is where we make that happen, okay? So these are conditional statements. Now, the big idea here is these are if-then statements that act as a single link, a single infallible piece of logic, right? You're saying, if this is true, then we know this is true. And that takes you from one place to another. And then what we can do is we can chain all those together. So if A leads us to B, and B leads us to C, and C leads us to D, and these are separate, discrete things like definitions, things we've proven in the past, things we've investigated and we know to be true, we can piece them all together and make a bigger thing like a theorem or a larger proof that says, if we ever now come across A, we now know that D is true. So that's the big idea here. We're going to create these single links of conditionals that say, if you are on A, then that for sure means B is true. Okay, so let's get started. Okay, so a conditional statement to start, we usually write it in if-then form. There's other ways you can write it. Okay, the if part that triggers the kind of condition to go forward, or the thing that you say, if this is true, then, that's called the hypothesis, okay? There's other words for it in other books often, like maybe the antecedent or things like that. But in our book, we're going to call it the hypothesis. And then the result, the thing that you say, then this must be true, that's called the conclusion, okay? But often we'll just do it with arrows. So we'll just say A implies B here, so A arrow B. Or sometimes, like when I was in graduate school, we used just double arrow, so like 2 lines. It doesn't matter which one. An arrow just means one implies the other, or you could literally just write the words A implies B. And obviously, I'm using A as a placeholder. This might be something like, if X equals 2, then X plus 1 is 3. So a really simple algebraic thing that we know to be true, but that's how you would write an if-then statement. Right? Okay, like if I get a haircut, then my hair will be shorter, or then I'll look amazing in the mirror. I don't know what, right? So you can create whatever if-then you want. All right, so validity of conditional statements. So basically what we're doing for the rest of the year is trying to prove things are true. That's much harder because there's infinitely many possibilities. If you say if something's a square then, you now have to investigate and prove every possible square that anybody could ever draw. That's a lot harder than proving a rule is false. To prove something's false, all you need to do is find one time when it's not true and go, ha, I just proved it's false. Right? So that's a lot easier. So that's what we're going to start with, is finding counterexamples to break rules. And that is a proof. That's a valid proof that something's false, and it's just a single example. So that's where we're going to start, because that's easier. Then we'll start piecing together conditionals later to prove things are true no matter what. And that's kind of the whole scope of this course you can look at in a few ways. All right, so to show that a statement is false, there's this truth table here. So saying like, if we have P implies Q, right? So we're saying if some like P, right? It's just a placeholder variable, then Q must be true. And so it's saying, okay, so if P is true and T is true, well, the whole statement's true then, right? So yes, P did get triggered and it did lead you to Q. So that's a valid statement. And then these down here, these other two are saying, well, if P is not true, right? If I say, and I'll give this example down below. If I say, if it's a sunny day then, and it's not a sunny day, well, that has nothing to do with your if-then statement, right? Your entire statement is saying if it's a sunny day. So it doesn't matter if it's a rainy day, a cloudy day. If it's not a sunny day, your statement isn't false because your statement has no correlation to what's happening, right? The only time you can say that statement is false is you're saying, if it's a sunny day, we go, oh, it is a sunny day. That's true. That's true. Then I'm gonna, I don't know, have some ice cream. And oh, I followed you the whole day with the little sneaky camera. You didn't have any ice cream. It was a sunny day. That was true. You said if it was sunny, then you'll have ice cream, and you did not. Liar, right? Then you would prove the statement is false. That's the only time, right? If it's not a sunny day, doesn't matter. And if it is a sunny day and I eat ice cream, well, that was a true statement. So there's only that one scenario when we have a true hypothesis, so the if did get triggered, and it was supposed to lead to the then conclusion, and it did not. it led to something else that was not that the conclusion ended up being false. Okay? So again, just an example here. So if it is sunny, I will go to the beach, right? So again, if it's not sunny, then who cares? These have nothing to do with my statement that if it is sunny, right? You go, oh, but you went to the beach on a rainy day. I go, cool, that was fun, but it had nothing to do with my statement about it being sunny. Okay? And then of these first two, if it is sunny and I do go to the beach, yeah, statement is still true. Statement is still true here. Statement is still true here. The only time you catch me out is if it's a sunny day and I'm not at the beach. You did not do what you said. It was sunny. Your statement got activated. It should have led to beach, and it did not. Okay? All right. So anyway, I won't repeat myself. All right. So now we're going to look at kind of permutations of conditional statements, because there's different ways we can massage it and play with it to just investigate logic, right? That's what we're doing in this whole class. We're just investigating logic. So first we can negate something, right? That just means the logical opposite. Now, I say to negate, that's like the verb, or the negation. I'll use either term depending on the sentence structure. But what it really means is just switching, right? So if it's true, we switch it to false. If it's false, we switch it to true. Or if I say, I will eat an apple, the negation is I will not eat an apple. Or if I say, like, I have a quarter, the negation is I do not have a quarter. So the easiest thing is just add the word not, right? Or if the word not's there, then take it away. Okay. So I give a simple example here. I will go to the pool. The negation of that is I will not go to the pool. Okay. So real simple. We use this symbol, which this symbol does come up later for other reasons, but in terms of logic and truth value, it means not. So this is some statement, I will go to the pool, and this is the opposite. I will not go to the pool. It is the not, the opposite, the negation of. Okay? So now let's look at different ways now using that negation that we could investigate this statement, okay? So if we have this original statement, we could play with it in a lot of different ways in terms of the logical flow. Is it forwards? Is it backwards? Are we talking about the opposite of one, the opposite of both? But there's three really common permutations that we use, and these are something you need to memorize. These are absolutely something that will show up on a quiz, on a test, and if you don't understand them well, you can get trapped in logical fallacies, and advertisements do this to you all the time. Like, you know, Disneyland, where dreams come true, and then you're like, well, so if I don't go to Disneyland, my dreams won't come true. And that's not it, right? And we'll look at what the name of that statement is, and that it's not actually logically equivalent. And so, but it's these hidden messages that you don't even realize you're thinking, but they influence your emotions and your psychology. So that's what we're kind of investigating here. So there's really three versions. So if we start with any original, right? So this is if something A, then something B, right? Well, the converse is we just flip that around, right? So if I say if it's sunny, then I will go to the beach. The converse is the reverse. So if I go to the beach, then it is sunny, right? And those are two logically different things, two different statements, and we'll investigate that later. Okay, the inverse is not A, then not B. So that would be, if it is not sunny, then I will not go to the beach. So it's the same direction as the original, if sunny, then beach, but it's not in front of both. So if not sunny, then not beach. I didn't flip the order or anything. Okay, and then the contrapositive, you switch the order and you negate both. Okay, so that's the original statement was that I'm using just out loud is sunny then beach. So this would be not beach. So we switch the order and not, then not sunny. Okay, something I just want to mention up here when we're talking about conditional statements at the beginning, the order actually doesn't matter here. So I could have said B, comma, if A. The if is still attached to the A, so this is still the hypothesis, and this is still the conclusion. It's whichever one has the if in front of it, regardless of order, right? The English language is kind of funky, right? You could do really anything you want with it, and then you just call it poetry or art, and you can use it in really abstract ways. But whichever one has the if, that's telling you what the hypothesis is, even if it's in reverse order. So the order would still be A implies B, because A is still the if portion. I just wanted to mention that as we go down here. Sometimes people, when we get to like Converse, they'll switch it around, but they'll leave the if. They'll be like, they'll be like beach if sunny. And so they'll move the if with the sunny. And so that's still the original. That's still if it's sunny, right? What you need to say is if beach, and now it needs to have a then in front of the sunny. So I just wanted to be clear on that. When you switch the order, you need to actually switch which one is with the if part and which one is with the then part. You can't take the if with it and just switch the order, because that's the same sentence. All right, so we've got these three different versions. We start with the original, and then we've got the converse, the inverse, and the contrapositive. Okay, so here's an example. I made a really easy one that's algebraic, as that's something you all come in knowing already. So if x is 3, then x squared equals 9. That's a true statement. X times x, 3 times 3 equals 9. Check. Okay, converse, so we switch the order. So now the converse, right, is just the arrow going the other direction. So if x squared is 9, then x equals 3. That is not necessarily true. It could have been -3. So you see what we did there? We took a true original statement and we tested the reverse order, and it wasn't true. And I'll get to kind of a different way to visualize when this is true or false in a minute. But let's just go through these, okay? So the inverse, we simply negate both, right? So the opposite of x equals 3 is x is not equal to 3. And there's even a symbol for not equal. I don't know if you used it that much in algebra, but you just literally put a slash to the equal sign, right? So that's not x equals 3. And then x squared is not equal to 9. So we just negate both. And then the contrapositive is now when you switch the order. So the x squared equals 9 is with the if now. And you negate both. So they're both a not. So this one has x squared is not equal to 9 and x is not equal to 3. Okay? So that's just a simple example. You're going to be asked to do that on the homework and on a quiz and a test. You might even be given a statement that doesn't have an if and then. You'll have to structure it as an if and then. And then you'll have to do the inverse, converse, contrapositive, test the validity, come up with counterexamples. So this is just kind of common problems you might be asked. And I'll do some examples later. Okay, so I just wanted to be clear, the converse is not the same as the original, right? So for example, here's one. If I'm given tickets to Disneyland, yeah, then I'll go to Disneyland, right? Somebody gives me tickets, I'll be like, all right, I'm showing up, right? But that does not mean that if I went to Disneyland, someone gave me tickets, right? I've been to Disneyland, I bought my own tickets. However, it is true that if somebody just gave me tickets, I would use them, right? So don't assume the converse is true. So the converse, remember, is just the opposite direction. So it might be absolutely true that if I'm given tickets, I'll go to Disneyland, but that does not mean if I went to Disneyland, we can assume that this happened. I could have gotten to that same conclusion a different way, right? A can lead to B, but maybe C also leads to B. So just because I got to B, it doesn't matter. We don't know where we came from. That's another way to visualize it, all right? But I really like spatially like two-dimensional representations, and so I love Venn diagrams, okay? Here's one way to think about it. Here's a specific thing, like if your dot is inside A, well then of course it's in B. That's true. So I just represented that as A implies B. So if I put a dot in A, then for sure it's in B. The converse of that though is if I put a dot in B, it's in A, which might be true. I might put a dot here that's in B and it's in A, but I might put a dot out here that's in B that's not in A. So really common what we have that where the original statement is true and the converse is not, it's because we start with a specific case of a more general situation. And you're like, okay, if you're specifically square, then you are a four-sided figure. But if you switch the converse around, you're saying if you're any four-sided figure, then you must be a square. The converse of that is not true. So often what that results in is people getting these logical fallacies. So I use that example here. Or if x equals 2, then it's any positive number, right? Specific to general, that's true. However, the opposite, if you're any positive number, then you must be 2. That's not true. So again, the converse is different than the original statement. Don't assume it's true. All right, well, what does it mean then for statements to be the same, right? I'm saying the original and the converse are not the same. What do I even mean the not the same? So logically equivalent means if one statement is true, then the other statement is true. If one statement is false, then the other statement is false. So they have the same logical truth value. So essentially they're the same statement, but maybe they're conveying different information, and it's useful to have two different statements, but they both have the same truth value. They're always true or they're always false. When one is false, the other is false. Essentially, they're tied, right? Those truth values are the same, okay? Now, really interesting is the original statement and the contrapositive are always logically equivalent. If the original statement is true, the contrapositive is true. And we're really in this whole class just going to deal with true conditional statements. What we're just trying to avoid is people making the jump from the original to the converse. That's the most common thing. Or sometimes you'll make the jump from the original to the inverse. But the original statement and the contrapositive are equivalent. Because if you think about it, right? If I've got this like perfect conditional statement that is totally valid, if I ever step on A, if that's ever true, then whoop, it just slides me over to B. Done 100% of the time. Well, all this statement says is, the contrapositive says, if you didn't get to B. Right? Well, think back to our statement. It says, if I step on A, I go right down this slide, zoop, to B 100% of the time. Anybody that steps on A, zoop, at B 100% of the time. And then this says, you didn't get to B. And we have this valid statement that says, if I step on the A button, zoop, I go to B. So if I'm not at B, then I could not have stepped on the A button, right? Because that for sure would have activated zoop, right over to the B, right? So that's why the contrapositive is true. It's simply saying if you didn't get to the end of a valid statement, well, then you never hit that starting value, right? Because 100% of the time that starting value would have taken you to B. So that's why those are the same. And then a cool consequence of that is these other two left over, other than the original and the contrapositive, actually end up being the same, because if you think about it, they're each other's contrapositive. So if we start with the converse, right? If this were our original statement and we wanted to make the contrapositive of it, we switch the order. So now the A goes first and the B goes second, and then we negate them both. So look at that. The converse gets taken over, gets taken over here, and its contrapositive is the inverse. So these come in a pair, right? The original statement and the contrapositive, always equivalent. And then the other two, the converse and the inverse, are also logically equivalent. But again, the key is the original and the converse are different. They are different logical statements. The logical flow forward is totally separate from the logical flow backwards. Okay. All right, well, what if we just knew both were true? If we knew the A implies B is true, and we knew the B implies A is true, so the forwards and the backwards are both valid statements, let's just combine those suckers into one, and we just put a double-headed arrow here, and we get this thing called a biconditional, right? So it's a conditional, and then bi means two, so it's two separate statements in one, and it's just an abbreviated way of saying it. So if A implies B, and if B implies A, we can just combine those to say A and B biconditional, and we use this term if and only if. And what that does is it essentially says A and B are equivalent. Okay, if A is true, B is true. If A is false, B is false. It doesn't matter which one I know, A or B, I then know the other one, right? It's like saying two variables, X and Y, have the same value. If I find X's value, boom, I know Y's. If I find Y's value, boom, I know X. That's the idea of biconditional, and it's really powerful. In fact, every single definition that we create in geometry has to be a biconditional, right? If I come across a right angle, then I know that right angle has a 90-degree measure. But the reverse must be true for it to be a good definition and not some vague whoopity waving your arms thing. If I ever come across a 90-degree angle, I need to know that's a right angle, right? It has to be specific enough and both directions. So right angle means 90, 90 means right angle. That's a good definition in geometry. Okay, same thing here. Congruent line segments means the segments have the same length. But if I come across segments with the same length, then I know they are congruent. That's a good definition. That was the definition of congruent line segments. Okay, and again, just to visualize as a Venn diagram, we cannot have a specific to general. This would be A implies B, right? So if I'm in A, then for sure I'm in B, but the reverse isn't true, right? I could put a dot in B that's not in A. And it can't be this one, B implies A, separate, right? So if I'm in B, for sure I'm in A. But the reverse, the converse isn't true, because if I'm in A, that doesn't mean I'm necessarily in B. It has to be that they're the same circle. They're the same region. The region of right angles is the same as the region of 90-degree angles. That's the same group of angles. Exactly. There's no leftover. There's no outside of the Venn diagram. It's all the intersection. It's all that middle portion. So that circle that is A is the exact same circle that is B. That's visually what's going on. Okay, let's just do some examples. Oh, that's pretty good. 20 minutes for the lesson. All right, let's do some examples. So identify the hypothesis and the conclusion. This is easy. So if, and then we just do everything after the if. This is the hypothesis. Then, and then this is the conclusion. And then if, so this is the hypothesis. Then, this is the conclusion. And then if, and you just circle everything other than the if, this is the hypothesis, then this is the conclusion. Now, I was kind of hoping they would try and trick us there and say something like, let's rewrite 6, the exact same word. This isn't the converse. This is the exact same statement with the exact same hypothesis, same conclusion, but just messing with the English language, because that's fun. So a hexagon, or let's say it is a hexagon, comma, if it has 6 sides. And then because we want to make it actually clear and readable, let's take the a polygon and put it at the beginning instead of an it, because what the heck is an it if we haven't started? So a polygon is a hexagon if. So notice it still has this if this, so this is still the hypothesis. And then there's no then, but this is the part that must be true after, so this is the conclusion. So it's always whatever is tied to the if statement is the hypothesis, regardless of order, okay? All right, so write each statement in if-then form. Let's just do 8 and 9. So the sum of the measures of supplementary angles is this. So this is like the resulting thing. So it's telling you like there's these supplementary angles, which means then that the sum is 180. So let's say if, so for 8, you could just go like plain math geometry and not make the English structure. You could just go like if supplementary angles, comma, then sum is 180, right? Or you could make it more readable. You could be like, if 2 angles are supplementary, comma, then the sum of their measures is 180, yada, yada, yada. So either one of these would totally work. I actually kind of prefer the first one. So if, get to the point, right? So if you have supplementary angles, then you get this 180, but you need to be clear and say that's the sum, right? The sum is 180. Each angle or the two, you have to be clear on that. So sum is 180. Okay, let's do number 9. So an angle formed by perpendicular lines. So that's the original start, right? So it's saying we start with this angle that's formed by perpendicular lines, then boom, the result is it's a right angle. So you just go if, and there's a symbol for perpendicular. Well, I guess we could just do that now. Why not? But I'll reintroduce it when we get to parallel perpendicular line. But the symbol for perpendicular is this, right? I mean, we can't do this because that's a plus sign. So it'd be ambiguous, and we don't do ambiguity in math. And so instead we just do half of it. We just do the sideways line and we go halfway. So that means perpendicular. For some reason, I don't know why, throughout the year, a lot of kids make up a symbol and call that bisect. Bisect doesn't have a symbol. Don't think that is bisect. I don't know why people do. That means perpendicular. So this means if perpendicular lines, comma, then the angles formed are 90 degrees. Boom. Oh, no. I misstated that. That's equivalent. 90 degrees and right angle. That's a biconditional definition. But we're just rewriting this. So are right angles. Boom. Okay, let's look at this. 40. Whoa, we jumped from number 9 to number 40. All right. So write the converse, inverse, and contrapositive. And then it says even, let's say whether it's true or false. And if it's false, let's freaking prove it, Let's use a counterexample. So let's go at 40. Okay, so if live in Dallas, then Texas. I'm abbreviating a little bit. So that's the original. So the converse would be if, and we just switch the order. So if Texas, then Dallas. Okay, the inverse, we negate both. So if not Dallas, then not Texas. It's a real test of your geography skills here, you guys. Okay, contra positive. And so this is where you switch the order. So Texas is going to come first with the if, and we negate it. So if not Texas, then not Dallas. Okay, so let's think about this. This is exactly the case of, we have a Venn diagram. The inner region is the city of Dallas, and that's in the state of Texas. So if we're in this Dallas, are we in Texas? Yeah, that's a true statement. So I'm going to switch colors here. And yes, I'm going to start with the original. So the original is true. Yes, okay. And then what about the converse? So if you're in Texas, are you necessarily in Dallas? No way. You could be in totally other places. So false, we need to come up with a counterexample. And let's say counterexample is Joe lives in Houston. Right? So there's another city. Joe lives in Houston. He lives in Texas. Houston's in Texas, but he does not live in Dallas. So our counterexample is someone that lives in Texas but does not live in Dallas. Boom. Got it. We just made our first proof there. Good job, team. Okay. Inverse. If you are not in Dallas, then you are not in Texas. Again, now just kind of cheating using past knowledge here, I know that the original and the contrapositive have the same value, and the converse and the inverse have the same value. So I'm already done. I already know the inverse is false, and I already know the converse is true. We're going to still investigate it, but that's how you know, right? That contrapositive is something has the same truth value. They're logically equivalent. So once I figure out the original and the converse, I'm done, right? But doing the others can help you double check. It's two different approaches, and then you compare and you go, whew, nice, they match up. I hope I'm doing well on this quiz or test today. Okay, so the inverse says if you're not in Dallas, then you're not in Texas. Okay, well, I could be again over here in Houston, and I am, what the heck, I'm totally in Texas. That is valid, or that is not true. I am not in Dallas, so I met the if statements hypothesis, and it led to a false conclusion. So that's the one-time counterexample, right? I have to trigger the if to be true, and then I have to lead it to a false conclusion. So I am not in Dallas, and yet I am in Texas. So again, a same example works. So Joe lives. What the heck is lives? Oh man, that's a cool sentence though. Lives in Houston. Okay. And then the last one, if you're not in Texas, then you're not in Dallas. That is true, right? If I'm outside of Texas, I cannot be in Dallas. Oh, unless you get really nitpicky and maybe they weren't talking about Dallas, Texas. Maybe you like Google some like Dallas other places and you're like, there's a Dallas in Alaska. So I found a counterexample. Let's not go there. You could nitpick, but let's assume the statement was if you live in Dallas, Texas, then you live in Texas, and it was specific to the Dallas we are talking about. Okay, let's look at one more. Let's do 42. So the sum of two complementary angles is 90. So the original is sum of two angles. Wait, what number? So 42. The sum of two complementary angles is 90. So this is if we are complementary angles, then sum is 90 degrees. Okay, that's the very definition of complementary angles. I spoiled it. I said it's the definition. What does that mean? Definition. That means it must be a biconditional. That means that all of them have to be true. What the heck? I spoiled all the fun. Let's investigate, okay? So let's do the converse. So the converse is if, and we just switch the order. So if sum of angles is 90 degrees, then complementary. And then the inverse, we negate both. So we say if not complementary angles, then not sum 90 degrees. And then the contrapositive, we switch the order and we negate. So we get if some angle's not 90 degrees, then not complementary. Okay, boom. And because we know this is the very definition of complementary angles, they are all true. That is 100% true, each one, right? If they're not complementary, then their sum is not 90, because if the sum was 90, they would have been complementary in the first place. Okay. Oh, I thought I had more. That's it, you guys. Hope you enjoyed the video.